Hey guys, so in this question, you have a parallel plate capacitor, and the distance between the plates of the parallel plate capacitor is given as 10 centimeters, right? So we have 10 centimeters over here of this parallel plate capacitor. You have two dielectric slabs of thickness, 5 centimeter each, and the dielectric constants are given as K1 is equal to 4 and K2 is equal to 4 and K1 is equal to 2, right? Both of them are 5 centimeters each, and they are inserted between the plates as shown in this figure. A potential difference of 100 volt is applied across the capacitor. So we need to find out how much net bound surface charge density will we have at the surface of the dielectrics, right? So if you're aware of the concept of bound charges in dielectrics, when we have a charge on the capacitors, you'll have induced charge on the dielectrics, which we can also count as bound charge. So we'll have to find out how much bound charge we'll have at the interface of the two dielectrics at this point, right? So there are two methods of dealing with this question. I'll go with one method and I'll give you the hint for the other method, which you can try solving using, which you can also try to solve this question. Okay, so let me go off with this approach right now. So let's say that because of your battery, this capacitor attains a charge Q, and then you have a charge minus Q on this. So we know that there will be an electric field being set up, right? So let that electric field be E naught bar when there was no dielectric. So because there's a dielectric right now, your field value will change. Your field in the first dielectric will be equal to E naught by K2. Your field in the second dielectric will be equal to E naught by K1, right? But I know that the potential difference between them should still be equal to 100 volts. So keeping this in mind, let me write this equation. So since your potential difference is equal to 100 volt, I'll say that E naught by K2 of 5 centimeters into 5 centimeters plus E naught by K1 into 5 centimeters has to be equal to 100 volt. So I basically written your relation between potential and field. So when I'm going from here to here, you'll have a potential drop of E into D. Similarly, here also you'll have a potential drop of E into D because field is uniform, right? So from this, we'll get what the value of E naught will be equal to. So substituting the values over here, I'll get E naught by 4 plus E naught by 2 into 5 centimeters, which can be written as 5 by 100 is equal to 100. So from this, we'll get E naught value. So this will become 3 E naught by 4 is equal to 1 by 20. This will become, so this will become 2000. So E naught value will be equal to 8000 by 3. Okay. So why have we calculated the E naught value over here? Because now after calculating the E naught value, what I'll be applying is Gauss law. What I'll be applying is Gauss law right now, and I'll be applying Gauss law over this surface. I'll be taking a Gaussian surface this way, right? So that's a diagram now which I'll try to draw here. So these are my two plates. These are my two plates. I need to find out what's your bound charge at the interface of the two dielectrics. So this is your first dielectric. This is your first dielectric. This is your second dielectric. This has K2 value. This is K1 value. So now the Gaussian surface I'm considering over here. The Gaussian surface which I'll be considering over here is something like this. It's also like a parallel plate, but a cuboid of this. So this is a Gaussian surface I'm selecting right now. Okay, so if you notice, you will have flux entering this Gaussian surface. This area also is A. Let me take this area to be A itself. I'll have field lines entering this Gaussian surface. I'll have field lines leaving this Gaussian surface as well, right? So I'll have a net flux, and that net flux should be equal to charge enclosed by epsilon naught. And this charge enclosed will basically be how much of a charge I'll have at the bound surface over here, right? So what is your net flux? Your net flux will be equal to minus E by K1 minus E by K2 into A plus E by K1 into A. So E naught was the notation I had used. So we minus E naught by K2 into A minus sign because this is field lines entering plus E naught by K1 into A because this is field lines exiting. And now that should be equal to charge enclosed by epsilon naught. So what will our charge enclosed value be equal to? Our charge enclosed value will be equal to, so minus E naught. We know the value of, so let me take E naught common. So it will be E naught A of 1 by K1 minus 1 by K2 into epsilon naught, right? And what we actually need is surface charge density. So actually, what we actually need is sigma enclosed. So what will sigma enclosed be equal to? It will be equal to E naught of 1 by K1 minus 1 by K2 into epsilon naught, which is equal to nothing but 8000 by 3 into 1 by K1 is 1 by 2 minus 1 by 4 of epsilon naught, right? So this value will turn out to be 4 minus 2, sorry, 2 minus 1, so 1 by 4. So your charge enclosed then will become equal to, or your surface charge density enclosed will become equal to 2000 by 3 epsilon naught. Right? So hopefully this question made sense. The other way of solving this question which you can try to do is, we treat this as two capacitors in series. And so we can say that this is made up of two capacitors C1 and C2 in series. And now you can find the charge on each capacitor. You can assume that there's a parallel plate over here. You can find the charge on each capacitor. They both will have the same charge. Q will be same for both of them. And then you can find out how much charge will you have how much induced charge will you have in each dielectric by making use of this formula, Q into 1 minus 1 by K, right? So hopefully this approach also makes sense. This is also a method you can try to get the answer for this, but I've gone with this method in this case, that is making use of Gauss law to get the answer, right? So hopefully this question made sense. See you guys in the next question.